Picture this. We've got an employee. Let's call her Priya. She's hanging out in a busy local coffee shop, sipping a latte, and trying to pull up a highly secure internal corporate HR dashboard on her laptop. Sounds like a totally everyday scenario, right? But just under the surface, an absolutely massive security challenge is unfolding. I mean, if anyone intercepts that traffic, company secrets are totally exposed. So today, we are going to follow the epic split-second journey of her single data packet to see exactly how it stays safe in such an inherently untrusted environment.
Welcome to this explainer. Today, we're taking those invisible, complex networking concepts and turning them into a visible, step-by-step journey. We are going to completely break down the anatomy of a WireGuard VPN tunnel. We'll track Priya's request from the exact millisecond her fingers hit the keyboard all the way to her company's internal servers and back again. All right, here's our roadmap. We're hitting the coffee shop dilemma, the VPN interface intercept, traversing the public internet, the critical trust boundary, arrival at the destination, and of course, the return trip. We're basically escorting a packet from a super vulnerable public Wi-Fi network straight into a locked-down corporate castle. To make this super easy to visualize, we're tracking this request across 4 primary environments. We kick things off right on Priya's local laptop at the user and app layer, dive down into our operating system, shoot out into the public internet transit, and finally land in the company's server processing environment. Step 1. The coffee shop dilemma and the vulnerable public web. Let's see exactly how this kicks off. So, the journey begins at the user and application layer. Priya opens her browser and types in her target, hr.internal.company.com. Her laptop immediately resolves this to a private internal IP address, 10.0.0.50, and her browser tries to open a standard TCP connection on port 443. Now, at this exact moment, her web browser has absolutely zero awareness of WireGuard or any VPN for that matter. It's totally oblivious. It just wants to send ordinary plaintext data to an internal IP, exactly as it would if she were sitting at her desk inside the corporate office. Step 2. The VPN interface intercept. It's time to reroute this packet. Since Priya isn't actually in the office, her operating system has to step in and play traffic cop before that plain text packet hits the coffee shop's totally vulnerable Wi-Fi router. Before anything even reaches the network card, the OS checks its routing table. Because her WireGuard client is running, there's a specific rule dictated by a setting called allowed IPs. The computer sees that the HR dashboard's IP, 10.0.0.50, falls squarely into the configured range of 10.0.0.0/24. Boom. Because of that match, the OS silently intercepts the packet, pulling it away from the dangerous Wi-Fi path and redirects it toward a very specific, secure destination on her own machine. That destination, it's the WG0 interface. Now, usually, when you think of a network interface, you picture a physical port you'd plug an Ethernet cable into, right? But WG0 isn't hardware at all. It is purely a piece of software running directly on Priya's laptop, acting as a secure virtual gateway. This is literally where the magic happens. The WOG0 interface immediately gets to work armoring Priya's data. It's already completed a rock-solid handshake with the company's server using the noise protocol and some heavy-duty math, curve 25519 keys. Using these keys, it encrypts the entire original packet. We're talking headers, payload, the whole shebang, locking it up with robust ChaCha20 Poly 1305 encryption. It's basically tossing the data into an unbreakable digital vault. But it doesn't stop there. It takes that newly encrypted, opaque blob and wraps it completely inside a brand new UDP packet. This new outer packet has a totally new destination, the company's actual public-facing VPN IP address, in our case, 203.0.113.9. hitting port 51820. Step 3. Traversing the public internet. The packet is finally leaving the laptop. Think of this as our X-ray view. On one hand, you have Priya's hidden true intention, securely accessing that internal HR server. But on the other hand, the only thing the coffee shop network, or literally anyone watching the public internet, can actually see is a generic, heavily encrypted UDP packet traveling to a public IP address. The reality is completely masked. Let's say some malicious actor is sitting at the next table over, snooping on the Wi-Fi. They are entirely locked out of the invisible side of this equation. No packet content, no idea the true destination is 10.0.0.50, and zero clue what app Priya is even using. All they can see is a secure stream of meaningless UDP data, the public destination IP of the VPN server, and the size and timing of the packets. That is it. Her internal data is completely dark to the outside world. Step 4. The critical trust boundary. We've finally arrived at the server. So the encrypted packet safely navigates all those internet hops and hits the company's VPN server. The server's own WG0 interface catches it and immediately runs through a rigorous, unforgiving checklist. First, who sent this? It checks Priya's identity by validating the sender against its strict list of known peer public keys. Next, it verifies the packet's timestamp counter. This is absolutely crucial to make sure someone isn't just capturing old packets and throwing them back at the server in a replay attack. Only after passing these strict tests does the server strip away the armor, decrypting the payload to finally recover Priya's original request destined for the HR server. And here is the absolutely crucial point. This exact millisecond of decryption is the critical trust boundary. It's the moment where security truly happens. Before this, nobody could read the traffic. But right here, right now, the traffic transitions from unreadable ciphertext back to vulnerable plaintext. The VPN server now knows exactly what is being requested, and from this second forward, the packet safety relies entirely on the internal network's own trust model. Step 5. Arrival at the destination. Let's get this packet to the HR dashboard. Now, holding that vulnerable plaintext packet, the VPN server essentially shifts gears and acts like a router. It checks its forwarding rules, sees that 10.0.0.50 is part of the internal corporate subnet it manages, and sends the packet onward into the private network. Quite often, it does this using network address translation, or NAT. This basically masks the packet's origin so that when it finally hits the HR server, it looks like a perfectly standard request coming from right inside the house. And the HR server, it is totally clueless, and that's exactly how we want it. From its point of view, it's just receiving an ordinary, trusted internal network connection attempt on port 443. It has absolutely no idea Priya is thousands of miles away sipping a latte. It inherently trusts that this traffic has already survived the network's rigorous access controls at the VPN layer, so it happily processes the request and starts generating the HR dashboard's login page. Step 6. The return trip. We've got to get that response back to Priya. You really have to appreciate the sheer speed and seamlessness of this system. The response follows the exact reverse path, perfectly mirroring the outbound journey in just milliseconds. The app server generates the plaintext response. Boom, millisecond 5. It hits the VPN server and gets re-encrypted into a secure WireGuard packet. Millisecond 25. It's flying across the public internet, completely opaque to onlookers. And by millisecond 40, it arrives back at Priya's laptop. Her WG0 interface instantly decrypts it, hands it to her browser, and the HR page renders as smoothly as if she were hardwired directly into the company mainframe. It's incredible. WireGuard elegantly and mathematically solves the massive headache of public internet transit, shielding your data from the most hostile Wi-Fi networks you can imagine. But it leaves us with this final incredibly provocative thought. If all this amazing encryption merely serves to safely deliver a packet to an internal trust boundary, what happens to an entire organization's security if just one server's peer list or a single internal routing rule is misconfigured? It's a sobering reminder that our impenetrable external armor is really only as strong as our soft internal organization. Definitely something to chew on until next time.